So I will be looking at Discrete Mathematics, an Open Introduction by Oscar Levin. And I'm going to begin with section 1, or rather chapter 1, Logic and Proofs, and section 1.1, Mathematical Statements. After completing this section, you should be able to do the following. Identify the logical structure of statements to determine their truth value in terms of the truth value of their parts. Identify the use of quantifiers in a statement and determine the truth value of the statement based on those quantifiers. And translate between statements in natural language and logical symbols. Okay, so it says, investigate. While walking through a fictional forest, you encounter 3 trolls guarding a bridge. Each is either a knight who always tells the truth or a knave who always lies. The trolls will not let you pass until you correctly identify each as either a knight or a knave. Each troll makes a single statement. Troll 1 says, if I am a knave, then there are exactly 2 knights here. Troll 2 says, Troll 1 is lying. And Troll 3 says, either we are all knaves, or at least one of us is a knight. Which troll is which? So we must ascertain who are the truth tellers and who are the liars among the 3 trolls. Well, let's see. Let's see, it says you can write here and it will be saved on this device, but your response will not be graded. Okay. And then it has instructor's feedback. I wonder if that's like an LLM or something. So if troll 1 is telling the truth, then and he's saying there are exactly 2. He's saying if I am a liar, then there are exactly 2 truth tellers here, which doesn't rule out the possibility. So how do we actually do this? How to do this? I never tried these sorts of problems. So let's suppose troll 1 is a knight. Suppose troll 1 is telling the truth. What does that imply? Oh, I guess. You know what? I think there are like 3 possibilities, right? And we have to figure out which of them is consistent. All right, so surely I can't just read straight through this. I have to analyze what I'm reading. So I'm going to open up a notepad and I'm going to get to it. And I kind of like it positioned on the left when I'm reading. And I'm going to have a real think through this problem. Not skipping anything. Really, I'm going to think through it. Okay, so knights and knaves both start with the letter K, which is not a good thing. And troll starts with the letter T. I'm going to say here's scenario 1. They're all truth tellers. And then, yeah, that's it. You would go through all these scenarios and then immediately rule out some of them, yeah? So TTT, TTF, TFT, and TFF, followed by FTT, FTF, FFT, and FFF. Probably there's some simple, clever way to do this, but I'm really very much a beginner at this, so I'm just going to see what works. Okay, they can't all be truth tellers, because otherwise that would be like contradiction, because troll 2 is declaring that troll 1 is lying, and if he's telling the truth, then that means troll 1 is not. So that's impossible. And in fact, it's impossible for the second one to be T, but the first one to be F, to be T as well. So that is also excluded, that one there. Okay. That's just an initial observation. And troll 3 is declaring either we are all liars or at least one of us is a knight. I really do think it comes down to this, like this is very significant. Okay, so if troll 2 troll 2 is saying troll 1 is a knave. That's what he's saying. So troll 2, if he's telling the truth, is literally saying troll 1 must be F. So they can't both be T. And if troll 2 is lying, then he's saying that troll 1 is lying, and he's lying about that. And therefore, the actual truth is that troll 1 is telling the truth. So they can't, the two initial can't both be false either. So that rules out those two. Okay. So now there's just 4 possibilities, I think. So troll 3 is saying okay, so let's consider the possibility that troll 1 is a liar and troll 2 is speaking truthfully about that. So that would be these two possibilities here. Now, if troll 1 is saying, if troll 1 is a liar, then he's lying about this statement. The statement being, if I am a liar, then there are exactly 2 knights here. And if you're lying about that, you're just simply saying it's not the case. We need to think. Troll 2 is telling the truth that troll 1 is a liar, and troll 1 is lying about this statement where he says, if I am a liar, then there are exactly 2 truth tellers here. And therefore, that one must be false. That can't be the case, because that would mean that he's a truth teller, because he's saying that those two are telling the truth. Okay. Troll 3 is making the simple statement that either they're all liars, or at least one of them is telling the truth, which is always true. That's always true, and therefore it must have T in this position. He can't be lying about that. Like, he can't be a liar. He can't be a liar, and therefore that excludes that one and that one. And so I think that this is the case. I think that troll 1 is a truth teller, troll 2 is a liar, and troll 3 is a truth teller. Now let's see if that's consistent. Okay, so troll 2 is a liar, and troll 2 is making the statement that troll 1 is lying. And he's lying about that, and therefore he's actually secretly making the statement that troll 1 is telling the truth. Okay. Now, if troll 1 is telling the truth, and he's saying, if I am a liar, then there are exactly 2 knights here. But it just so happens to be the case that he's not a liar. It doesn't rule out the possibility that there could also be 2 truth tellers. Just because he happens to not be a liar, it doesn't rule out that possibility. And troll 3 is making the always true statement that either they're all liars or at least one of them is a truth teller. So I think this is the best bet. So I think that troll 1 is a knight, troll 2 is a knave, troll 3 is a knight. This is consistent. Troll 3 is making a tautological, always true statement. Troll 2 is saying troll 1 is a liar, but lying about that. Troll 1 is telling the truth. And it's possible troll 1 to make their claim about being a liar without it excluding the analogous claim as a truth teller. That's what I think. Oh man, is that what it does? All right, I guess that'll have to just be left like that. Okay, now it goes on to say, in order to do mathematics, we we must be able to talk and write about mathematics. Perhaps your experience with mathematics so far has mostly involved numerical answers to problems. As we embark towards more advanced and abstract mathematics, writing will play a more prominent role in the mathematical process. In fact, the primary goal of mathematics as an academic discipline in its own right is to establish general mathematical truths. How can we know whether these facts, perhaps called theorems or propositions, are true? We construct valid arguments called proofs, which establish the truth of the statements. Here, an argument is not the sort of thing you have with your mum when you disagree about what to have for dinner. Rather, we have a technical definition of the term. Definition. An argument is a sequence of statements, the last of which is called the conclusion, and the rest of which are called premises or premises. An argument is said to be valid provided the conclusion must be true whenever the premises are all true. An argument is invalid if it is not valid. That is, all the premises can be true and the conclusion could still be false. An argument is sound provided it is valid and all the premises are true. A proof of a statement is a sound argument whose conclusion is the statement. Right, so let's see about understanding that. So I haven't titled my notes as of yet, so I best do that now. So this is section 1.1, mathematical statements. And that right there is just an opening investigation. Next, I'm going to think about these words and what they mean and really try to get a grip on what they mean. Okay, so I get that an argument is a sequence of statements which are called premises, and the last statement is called the conclusion. I get that. An argument is said to be valid provided the conclusion must be true whenever the premises are all true. Okay, so for example, if I say, all men are elephants, that's premise one. Premise two is elephants can walk on water. And then premise three is I am a man. My conclusion is that I can walk on water. Now, all three of those premises are false. The first one being that, no, sorry, only the first two are false. Only the first two premises are false, but the third premise is true. But if all the premises were true, then the conclusion necessarily follows. It necessarily follows that that me being a man would put me in the category of elephants, and me being an elephant would put me in the category of those who can walk on water. And so that's what validity points to. That's what validity points to. And otherwise, an argument is invalid. And an argument's soundness points to whether the premises are true or not. Whether the premises are true or not. So here's an argument that is, so I just gave an example of an argument that is valid but unsound. And now I will give an example of an argument that is invalid but sound. Here we go. Premise 1, I am a man. Premise 2, the Earth orbits the Sun. Premise 3, 2 plus 2 equals 4. Conclusion. Conclusion, 1 times 1 equals 1. That conclusion in no way follows from those premises, even though they're all true. So I would say that that's a sound argument, but it's invalid. And the special kind of argument is when it's sound and valid. And that would be a proof. That's called a proof of a statement that is a conclusion at the end. Okay, so I think I understand that now. So I'm just going to say validity versus soundness. By the way, to determine whether we have a proof of a statement, we must decide both whether every premise is true and whether the argument is valid, whether the conclusion follows from the premises. So how can we do this? Consider the following 2 arguments. If Edith eats her vegetables, then she can have a cookie. Edith eats her vegetables. Therefore, Edith gets a cookie. Florence must eat her vegetables to get a cookie. Florence eats her vegetables. Therefore, Florence gets a cookie. That little symbol there with the 3 dots, like a position like the vertices of a triangle, means therefore. And if we're upside down, then it would symbolize because. Now, are these arguments valid? Yes, the first argument is valid, and it's instantiating modus ponens, I believe. It's saying if P, then Q, P, therefore Q. Although someone could quibble and say she can have a cookie is distinct from she gets a cookie. But assuming that these 2 mean the same, her having the permission to have a cookie, meaning that she actually gets one, assuming they're the same, then it's valid. Next, similar remarks apply, and I would say that that's valid. I'm much more confident about the validity of the second argument than I am about the first argument. But now we're going to see. Oh, that's interesting. Look at that. Okay, so I got that wrong. And I need to articulate why I got that wrong. Notice, this says if P, then Q. But this does not say if P, then Q. This just says Florence must eat her vegetables to get a cookie. For all I know, there are other requirements for her to get a cookie. So, okay. Here's a remark. The arguments in the example above illustrate another important point. Even if you don't care about the advancement of human knowledge in the field of mathematics, becoming skilled at analyzing arguments is useful. And even if you don't want to give your grandmother a cookie, if you are using mathematics to solve problems in some other discipline, it is still necessary to demonstrate that your solution is correct. You better have a good argument, that is. Since arguments are built up of statements, we must agree on what counts as a statement. Definition. A statement is a declarative sentence that is either true or false. If the sentences in an argument could not be true or false, there would be no way to determine whether the argument was valid, since validity describes a relationship between the truth values of the premises and conclusions. The goal of this section is to explore the different shapes a statement can take. We will see that more complicated statements can be built up from simpler ones in ways that entirely determine their truth value based on the truth value of their parts. Preview activity. Before reading on the main content of the section, complete this preview activity to start thinking about the types of questions this section will address. Which of the following sentences should count as statements? That is, for which of these sentences below could you potentially claim the sentence was either true or false? Okay. For statement 1, this does not apply as it's a question. For statement 2, this does apply, and in fact, it's actually true. Statement C, all right, did I say statement 1 and 2? Statement A and B, okay. Statement C, well, that's a question, so it doesn't apply. Statement D is pointing to a variable or value, but it's not something to which we could say, true or false. So that one, it doesn't apply. And statement E says the sum of the first 100 positive integers is 17. That's false, but it is a statement. And that's correct, and that's good. Okay. Question 2. You and your roommate are arguing, and they make the audacious claim that pineapple is good both on pizza and in smoothies. Which of the following are reasonable responses to this claim from a logical point of view? So, A, the statement is false because while pineapple is good on pizza and pineapple is good in smoothies, a pizza smoothie is never good. That doesn't logically follow. B, the statement is half true because regardless of what you think about pineapple on pizza, we can all agree at least that pineapple is good in smoothies. I don't think that one applies. The statement is C, the statement is false because even though pineapple is good in smoothies, it is not good on pizza. And D, the statement is false because everyone who likes pineapple on pizza does not like pineapple in smoothies. Okay, I don't think any of these statements can be applied but I'm about to be educated. Two of them apply. Okay. They make the audacious claim that pineapple is good both on pizza and in smoothies. All right, so I think the last two sort of resemble logical statements. Oh, I get it. So the speaker is sort of coming from their own point of view. Right, I understand. Okay, question 3. Your roommate now makes an even more outrageous claim. If a superhero movie is part of the Marvel Cinematic Universe, then it is good. Which of the following are reasonable responses to this claim from a logical point of view? A, the statement is false because there is at least one superhero movie that is part of the Marvel Cinematic Universe that is also not good. That's logical. If you believe that, that's logical. This is false because there are good superhero movies like Wonder Woman and Dark Knight that are based on DC Comics and so not part of the Marvel Cinematic Universe. That's not relevant. The statement is false because, for example, Green Lantern is neither Marvel nor good. No, because it's making a claim about superhero movies that are part of the Marvel Cinematic Universe. And D, the statement is true because more than half of the Marvel movies are good. Okay, so that one I got right. It was statement A. Question 4. Your roommate just won't let up with our outrageous claims. Now they claim that every troll is a knave, and there is at least one troll that is a knight. They claim that either every troll is a knave, or there is at least one troll that is a knight. What can you say to this? I would say, yes, this is true because every troll is either a knight or a knave. If it is not the case that all trolls are knaves, then there must be some troll that is a knight. So I believe it's statement B. Right. Next up, atomic and molecular statements. A statement is any declarative sentence which is either true or false. A statement is atomic if it cannot be divided into smaller elements. Otherwise, it is called molecular. For example, these are statements that are atomic. Telephone numbers in the USA have 10 digits. The moon is made of cheese. 42 is a perfect square. Every even number greater than 2 can be expressed as a sum of 2 primes. And 3 plus 7 equals 12. So I know that the second, third, and fifth statements are false. I don't know about the first one, but I know that it is either true or false. And for the fourth one, that is a famous unresolved conjecture in number theory called the Goldbach conjecture. And then it says, no, these are not statements. Would you like some cake? The sum of 2 squares. 1 add 3 add 5 add 7, all the way up to 2 and add 1. Go to your room, and 3 plus x equals 7. So let's think about why they're not statements. The first is an interrogative. It's a question. It's a question. It can be answered with a statement, like a yes or a no, but it doesn't have a truth value inherently associated with it. Statement two, statement two, I guess I might say expression two or sentence two. Yeah, I could say sentence two is just naming something. Similar to sentence three. Sentence four is an imperative. It's telling you to do something. And that's neither true nor false. Although you do either follow the command or you don't. So I could see why somebody might be confused about that. And finally, statement five, 3 at x equals 12. Well, I would kind of disagree with them a little bit about that, depending on what x actually refers to. Okay. Now, they say the reason the sentence 3 at x equals 12 is not a statement is that it contains a variable. Depending on what x is, the sentence is either true or false, but right now it is neither. One way to make the sentence into a statement is to specify the value of the variable in some way. This can be done by setting a specific substitution. For example, 3 at x equals 12, where x equals 9, which is a true statement. Or you could capture the free variable by quantifying over it, as in, for all values of x, 3 plus x equals 12, which is false. But nonetheless, it turns it into a statement. We will discuss quantifiers in much more detail in the subsection quantifiers and predicates below. You can build more complicated molecular statements out of simpler atomic or molecular ones using logical connectives. For example, this is a molecular statement. Telephone numbers in the USA have 10 digits, and 42 is a perfect square. It's a conjunction of two atomic statements from the list above, both of which are false. And a conjunction of two false atomic statements is itself false. Note that we can break this down into two smaller statements. The two shorter statements are connected by an and. We will consider 5 connectives and, such as in Sam is a man and Chris is a woman, or like in Sam is a man or Chris is a woman. If then, that's a single logical connective. If Sam is a man, then Chris is a woman. If and only if, which is again a single logical connective, as in Sam is a man, if and only if Chris is a woman. And finally, not, as in Sam is not a man. The first 4 that I listed there, and, or, if, then, and if and only if, those first 4 are called binary connectives because they connect 2 statements, while not is an example of a unary connective, since it applies to a single statement. These molecular statements are, of course, still statements, so they must be either true or false. The crucial observation here is that which truth value the molecular statement achieves is completely determined by the type of connective and the truth values of the parts. We do not need to know what the parts actually say or whether they have some material connection to each other, only whether those parts are true or false. To analyze logical connectives, it is enough to consider propositional variables, sometimes called sentential variables. Usually capital letters in the middle of the alphabet, like P, Q, R, and S. We think of these as standing in for usually atomic statements, but there are only 2 values the variables can achieve, true or false. We also have symbols for the logical connectives. Wedge. What's this upside down V? What's this V called? I think it's called vel, right? But the implication arrow, the biconditional arrow, and the negation sort of symbol here. I don't know what the actual precise names are of the symbols, but I know what they're talking about. So, new definition. We define the logical connectives. Read this as P and Q, and it's called conjunction. You read this as P or Q, and it's called disjunction. You read this as P if P then Q. I've also heard P implies Q, and it's called implication or conditional. And you read this as P if and only if Q, which is called a biconditional. And this is read as not P, and it's called a negation. As stated, the truth value of a statement is determined by the truth values of its parts, depending on the connectives. The truth conditions for the logical connectives are defined as follows. P and Q is true when both P and Q are true. I would say only when both P and Q are true, but they can phrase that how they like. P or Q is true when P or Q or both are true. P implies Q is true when P is false or Q is true or both. I think actually the implication binary connective, logical connective, is better captured by a truth table, as we're about to see. And P, if and only if Q, is true when P and Q are both true or both false. And not P is true when P is false. Each of the above definitions can be represented in a table called a truth table. We simply list what the truth value of the statement is for each possible combination of truth values of the parts. For example, we can use the truth table for P implies Q to decide whether the statement, if 5 is even, then 6 is even, is true or false. Here, P is the statement, 5 is even, and Q is the statement, 6 is even. Since 5 is not even, the statement P is false. And since 6 is even, the statement Q is true. The truth table tells us that the statement P implies Q is true when P is false and Q is true. So the statement if 5 is even, then 6 is even is true. If you don't like that the statement is true, hold on to that thought and we will hopefully resolve it soon. Note that for us, or is the inclusive or, not the sometimes used exclusive or, meaning that P or Q is true when P or Q or both P and Q are true. As for the other connectives, and behaves as you would expect, as does negation. The biconditional, if and only if, might seem a little strange, but you should think of this as saying that the two parts of the statements are equivalent in that they have the same truth value. This leaves only the implication P implies Q, which has a slightly different meaning in mathematics than in ordinary usage. However, implications are so common and useful in mathematics that we must develop a fluency with their use, which warrants a whole section. Using the truth conditions for the logical connectives, determine which of the statements below are true and which are false. Okay, so (17) is prime and 17 is odd. Drew, 17 is prime and 18 is prime. Well, that's true and that's false, and they're connected by a conjunction, so it's false. 17 is prime or 18 is prime. That's true, that's false, connected by a disjunction, and therefore it evaluates as true, because only one of them has to be true, one of the atomic statements. 17 is prime or 19 is prime. Well, they're both true, so that's fine. If 17 is prime, then 19 is prime. A truth implies a truth. It sure does. If 18 is prime, then my favorite number is 17. Okay, this is false. The antecedent is false. And I have no idea if their statement is false, so I'm going to put a question mark. 17 is prime if and only if 19 is prime. Because those two atomic statements are true, the biconditional evaluates as true. 17 is not prime if and only if 19 is not prime. That's false, and that's false. Notice, though, the atomic statement is 17 is prime, and the other atomic statement is 19 is prime. This is a negation, and this is a negation, and this is a biconditional connecting them. So it's a molecule. It's a molecular statement with 3 logical connectives. But anyway, it evaluates as true. So the sixth one, I don't know. Right, okay. Hold on. If 18 is prime, then my favorite number is 17. A falsehood always implies a truth. I get it. So until now, I hadn't properly applied my knowledge of the conditional. I just known about it in the abstract, like algebraically. But now I've actually applied it, and that's good. The way we define logical connectives and their truth value is very precise and technical. Often, language is not. Part of learning how to communicate mathematics is learning the cultural norms of mathematical language and how to translate statements in ordinary language into these technical statements. This will get easier with practice, so make sure you are talking to lots of people about the math you are studying. Here are a few examples of how ordinary language might be difficult to translate. Identify the logical structure of each of the following statements. 1. 4 and 5 are both prime. So I believe it's making the claim 4 is prime and 5 is prime. 2. Only one of 4 or 5 is prime. So I believe it's making the claim 4 is prime and 5 is not prime. Wait. What actually? I mean, I know it's making the exclusive OR claim, so I have to only know how to express that in terms of exclusive OR. 3, you must attend class. You must attend every day and do the homework to pass this class. Don't quite know what how I could assess the logical structure of that. if you attend class every day and do the homework, if you do not attend class every day and do not do the homework, this implies you will not pass. Something like that. For every number is even or odd. So let's see, I'm kind of curious about this. Interesting. Okay, so we're up to quantifiers and predicates. And I guess then we get to exercises. So this was just a demo run of seeing if I could read out these sections and how long it takes and what it feels like to do so, and if it's actually productive or not. Might continue this, I might not. Anyway, be well, be well.